My name's Dan Baston. I'm a software engineer at a company in Vermont called iSciences, and we do consulting primarily for the federal government in areas of water, climate, and security. But if you've run into me before, it's more likely on open source work I do. So I got started about 10 years ago with OSGeo projects, contributing to PostGIS, and that's kind of evolved over time, and now most of what I do is maintenance work on the GEOS and GDAL libraries. The talk I have today is about none of those things, actually. It's a library I put together called exactextract for doing raster vector zonal statistics. And what I mean by that is really anytime we have raster or gridded data sets and we want to transfer some information from those data sets onto a vector-based data set like polygons or lines. So often, gridded data sets we're dealing with are things like weather data or modeled outputs, things like land cover or population data. And we just want to combine those with vector data sets like administrative areas or watersheds to look at questions like how much precipitation is falling in each watershed, what percentage of this area is or this network is experiencing freezing temperatures, questions like that. And when you look at how these stats are computed, I think of this as kind of like a form of a spatial join, but it's a little different than a vector-vector spatial join, in that the core libraries in the stack don't really handle this. So you might think that functionality like this would live in GDAL, but it has a little bit too much vector stuff going on to really fit well in GDAL. You might think it belongs in GEOS, but GEOS doesn't really have abstractions around raster data, so it hasn't landed there either. The result of this is that there are a lot of implementations of this kind of higher up in the stack. So QGIS, GRASS, PostGIS, they all have their own implementations of zonal stats. And we see Python packages like raster stats. We see various R packages doing the same thing. Here I am talking about another. All the packages that are out there that I've come across really approach this in one of a few different ways. So the simplest one is to take this problem of mapping vector data to raster data and convert it into a vector-vector problem. So instead of raster cells, we just take the centroid of each pixel, and we do a whole bunch of point-in-polygon tests to relate that to the vector boundaries that we're interested in. So this can get pretty compute intensive if we have a lot of points. And it's really just an approximate result. Depending on the shape and size of our polygons, we may miss pixels that we really should be including in our analysis, or we may pick up pixels that really only a small part of that pixel is associated with our boundary. This method is used by QGIS as an example, and it's also implemented or available in PostGIS. The other common way to come at the problem is sort of the inverse. So we just make it fully a raster problem. We convert our polygons or our lines into rasters. And this gives us a little more flexibility. Like if we're using GDAL to rasterize something, we have some options. We can either, I guess by default, end up with something that's pretty much equivalent to the point-in-polygon method, where if the cell center would be inside the polygon, then we burn that into the raster. We also have the option of including all pixels that touch the polygon anywhere. But you still run into cases where neither one of these does really well, and here's a couple that I just keep on hand. So small polygons, so here we're looking at 4 islands in the Indian Ocean, the Comoros and Eel-Mayotte. And we see that with the point-in-polygon method or default rasterization, we're only going to pick up 1 pixel that's associated with one of those islands. And if we use the all-touched option for rasterizing our polygons, then we pick up our whole input area, but we also pick up a lot of ocean area that may not represent very well the conditions on those islands. I think it might have been an example like this that sent me down the whole rabbit hole of this problem in the first place. So this is a lake polygon from a reservoir in Russia, and you can see that by default we would pick up these 3 pixels on the left to represent that polygon. And if we do rasterize with all touched pixels, we get all the pixels on the right. So we cover our whole area, but we include a lot of area that has nothing to do with our lake in question. And then another category that I think is kind of interesting is polygons that don't have a weird shape at all, but they're oriented kind of at 45 degrees to our grid. So in cases like this, we're either going to pick up too few pixels, like on the left, or we're going to end up with a lot of extra pixels, like we do on the right. So to kind of combat this, there's a third method out there, which it's available in PostGIS, and it's also available in QGIS for really small polygons. I think in QGIS, if your polygon touches fewer than 2 pixels, it's going to detect that and switch over to this. What we do in this case is take each pixel and convert it into a rectangular polygon. Then we use our basic polygon operations like st-intersection and PostGIS to figure out that intersecting area, what its shape is, and what fraction of the pixel is covered. So this gives us a nice, accurate result. It is also really, really slow. So you don't see this used in the wild too often. So when I got into this problem, I kind of came up with this wish list of what I would like a better solution to do. One is I want to be able to handle arbitrarily large polygons and rasters. So we work a lot with global data sets, ugly country boundaries with lots of coastlines. I want to be able to throw huge stuff into this as well as tiny little polygons and get an accurate result and just not think about those scale issues. It also has to be really fast because a lot of the data I'm working with is weather or climate model outputs, and it's really highly dimensional. So we might be looking at multiple weather models, multiple parameterizations of those models, multiple parameters, right? We want temp and precip and so forth. And then we're going to be looking at a whole number of forecast time steps. So this is really like an inner loop operation. If we can make it 10% faster, that's still a win. Fortunately, we can do a lot better than that. And another piece that comes up often for us is wanting to incorporate a weighting raster. So rather than just looking at the average of a raster, say average precipitation over an area, we want to look at a population weighted average. So we had a project with electrical grid demand areas. You want to predict electricity usage. Well, if that's driven by heating and cooling, it's really important to look at the weather conditions where people actually live. And so the result of all of this, and a lot of messing around, is this library that I called exactextract. And it's really a fast version of method 3 that I showed before. So it's going to come up with the same result as taking each pixel and converting it into a polygon and doing that intersection calculation. But instead of using a generic intersection calculation like we have in a library like Geos, it does its own thing, which is really not that complex. When I started getting into this, it was one of those like, well, why don't you just type questions? And usually there's a reason, why don't you just? But this is a case where it actually seemed to work out pretty simply. So you take your polygon and you just walk along that boundary and you keep track of when it enters and exits each grid cell. And that's really easy to do because we're just talking about rectangles here. I can't handle hexagons or rotated grids. This is just straight up rectangles. And after walking the boundary of the polygon, what you've ended up with is the set of pixels that are partially covered by the polygon. And you can do some math after the fact to figure out what that fraction covered is, or reconstruct that shape if you need to. And then for all the pixels that are left, you know that they're either entirely in or entirely out. And you can do just a handful of point-in-polygon tests. And once can you see my mouse? Yeah. Once you know that this pixel is out, you can use a flood fill, like the bucket tool in Paint, to propagate that status throughout the rest of that region. So in this case here, you would only need 4 point-in-polygon tests to basically determine the whole matrix here. So this works out to be really fast. And in addition, we're getting more information. So back to that reservoir example, the output of exactextract is going to be for each of those cells what fraction of the pixel is covered by your polygon. Or if you're dealing with linear data, what is the length of lines within that cell. To use this, it's actually been available in an R package since 2019, but only recently like last week, did I publish a Python interface for this. There's also a command line interface too. And on the Python side, I want to say that I'm really grateful to both Vincent and Daryl, who, as far as I'm concerned, just popped out of nowhere and said, hey, it looks like you have a cool package. Here's everything you need to publish that on PyPI or CondaForge. So I was kind of dreading, getting into Python packaging, and it was just magical for these guys to show up out of nowhere and hand that to me. To use this, it's pretty simple, so I don't need to spend a lot of time on it, and it's going to be pretty much the same whether you're on command line, Python, or R. You're just going to point it to some source of rasters. So if you're in Python, that could be a file name that could be opened with GDAL. It could be an X-array data set, kind of whatever. And with polygons, it just needs to be something readable by GDAL. You give it your rasters, your polygon, and one of any number of canned stats that you want to calculate, or you can do more than one stat at a time too. And it can give you back a data frame with the results of that operation. If the built-in stuff doesn't cover your needs, you can give it a custom function in R or Python. So here we're just saying, well, let's get the mean value of all pixels that are more than 50% covered by the polygon. You can also just dump out all the pixel values and the fraction covered as a table, if you want to work with it in some other environment. And finally, it handles weighting, weighting rasters. If you have multiple rasters whose grids are basically compatible, like if one nests in the other. So here we're taking a 2.5-minute global temperature grid, a 30-second population grid, and outputting that population weighted mean temperature for each state at a given point in time. And just as an aside, I guess I kind of already mentioned this with the electrical grid example, but it really does make a difference in a lot of cases to bring population into account. I guess that's pretty obvious, but with exactextract making that really easy to do, you might want to consider that in cases where you otherwise wouldn't work with population data. So I said this is fast. Here are some benchmarks, and I want to preface this by saying that performance of this stuff is really complicated, and it depends on, the resolution of your raster and what format it's stored in, what compression scheme is used, how complex are your polygons, how large are they, and how disparate are they? Do you have a lot of cases like the US or Russia where your bounding box spans the globe, or France where you have, also spanning the globe in a very sparse way. But here's just one example. So this is natural Earth country boundaries at their highest level of detail, the gridded population of the world data set at 30 seconds, and on the right, I'm just comparing the runtime between exactextract, QGIS, and the Python raster stats module. So in this case, it makes quite a big difference while also giving a more precise result, I guess. If we drop the resolution of that population grid, we see, same general pattern, but some slight differences. So this is why I can't say, it's X% faster, because it really depends. And in another case here, where we're looking at a single Landsat scene with some watershed boundaries, in this case, it's only slightly faster than the raster stats module, which is using rasterization. It's been looked at, there's a couple other benchmarks I found floating around on GitHub where people have found generally the same conclusions, but it's really something you would want to check with your own data. Now, despite performance being variable, that in the testing I've done, I can generally say that your runtime is split between this calculation of the fraction of each pixel that's covered and reading those pixel values themselves. That's if you're reading one raster band. If you start talking about many raster bands, then it really quickly becomes just an I/O problem. How can you most efficiently read these pixel values for all the areas that you need to cover? One thing people ask me is, well, can you persist these coverage fractions? Can you store them in a file? I haven't found a case where that would really be helpful, because why would you want to save them? Well, it's either because you have large polygons, and in that case, storing that is going to add a lot of I/O, or you have many bands or many rasters, and then in that case, this calculation step isn't really significant in the first place. But if someone can come up with a case where this matters, I'd be interested to check it out. To help manage the I/O, there's a couple different strategies that the library offers. So one is what I call the feature sequential strategy. So we just iterate over the features. We process them one at a time. We can stream everything in memory. And for each feature, we find the corresponding raster cells. We update our stats and write that to disk or wherever. The other is the raster sequential strategy. So we load all the features at once. We iterate over blocks of the raster, find which features intersect, and when we're all done, we can write everything to disk. So just showing what that would look like, looking at states in Australia with the feature sequential strategy. We hop around a bit. We're sensitive to the order of features, the order that they happen to be in our input data source. We end up reading pixels multiple times. If we have a large feature, we can automatically break it up to avoid reading too many pixels in memory at once. That's how I say we can handle data of any size. And then with the raster sequential strategy, we would just iterate over blocks of the raster. So we're never going to read a pixel more than once, but we're going to end up visiting each of these polygons more than once. So that can be a bit slower or faster. It all depends. A couple tips I have. Now, I was in a talk yesterday where the speaker said, everything comes down to data to your chunking. And that was in a completely different context, having nothing to do with this. But I'm going to say here that my #1 tip is to pay attention to your data chunking. And so one of the kind of pathological cases I came across was this NOAA data set of monthly mean temperatures for the US at 2.5-minute resolution. So this comes in one big netcdf file. It's got 1,500 bands. And the chunk size is an entire band. So often you would see a raster that's written in either scan lines or tiles. Here the entire band is one chunk. And that means if you want to read any piece of that, you have to decompress the entire chunk. And so processing this data set of Florida counties, there's only 67. That took like 20 minutes, which is just nuts. So when I looked into what was going on, it comes down to the behavior of the GDAL block cache. And if you're not familiar with that, so the way GDAL works is when it has to decompress raster data, it's going to store that in a cache in memory so that if you ask for it again, it's not going to have to repeat the decompression. By default, that's allowed 5% of your RAM. There's a configuration option for that, just like there's configuration options for 1,900 other things. And when that cache is full, old blocks are evicted. And so what happens here, when your block size is really huge, when we go to each feature, we need to read those bands one by one. So we start filling that cache up, and then we start evicting that cache from that cache before we even get onto the second feature. So every feature you process has to decompress that entire raster of 1,500 bands. So there's several fixes for this. So you could use the raster sequential strategy that I mentioned. That will ensure that you only decompress stuff once. You could take that input data set and re-chunk it. So you could re-chunk it to use scan lines or tiles. Those would make it about 30% larger. So from like a data provider perspective, I see why they distribute it the way they do. Or if you have memory to spare, you could just increase your GDAL cache size. And any of these little tweaks is gonna take your runtime from, in this case, 24 minutes to 7 to 30 seconds, depending on which of the choices you made. Another tip is to avoid bringing all of your polygons into memory if you don't need to. So, if you're used to working with something like GeoPandas, your first step might be take your data set and read it into a data frame. Since exactextract really just wants to see the features one at a time, you don't need to load that all into memory. You could save that memory for your GDAL cache, for example. So if you go old school, use your GDAL Python bindings, now you don't have anything unnecessary in memory. You're just going to look at those features one at a time. And if you need to reproject, I feel kind of weird being up here in 2024 and saying XML is the solution. But XML is the solution. I think a fair number of people may be familiar with GDAL's virtual raster format, where instead of actually reprojecting a raster, you write an XML file, or it generates one for you that describes that reprojection. There's also a vector version of that, and I think it's less used because you have to actually write this XML for you. Like OGR to OGR won't do it for you. But it's pretty simple. You know, you just say, I have this source data source. I want to reproject it to this, this projection. And now when I open that up with my GDAL Python bindings, it's going to reproject those features on the fly, so I don't have to bring them all into memory. If your stats are generating a lot of data, you also don't want your results sitting around in memory. Like if you want to extract all the pixel values, say, for every polygon, you want to be streaming that stuff out to some data source, or data sink, I guess, as you go. So exactextract has an option, you know, instead of getting this back as a data frame, you can say, I want GDAL to handle the output, and this is where I want it to go. So this example here is using GDAL to connect to a PostGIS database, issue a query, read those results one at a time, and then write the results back to the database as they're processed. A couple other applications for this library that are, you know, I think are out there but are a little less developed are fuzzy rasterization. So being able to take a polygon and instead of getting a mask back of it's here, it's not here, you can get back those coverage percentages directly and write that to a raster. So that's available in the R package. I haven't exposed that in Python yet. I'll see how my train ride home goes, and you know, it may well land pretty soon. Another interesting case that I've run across is maximum overlap rasterization. So usually when you're rasterizing a set of polygons, you know, the way GDAL is going to do it anyway is it's going to come to a polygon, find out the intersecting pixels, and burn in some field from that polygon into the raster. So you're sensitive to the order that the features come in, right? So if you are, I think of Angola and Zambia, right, side by side. So if you've got a pixel that is, okay, if you've got a pixel that is 99% in Angola and 1% in Zambia, if your polygons are in alphabetical order, you're going to call that pixel Zambia. What exactextract will let you do is assign that pixel to the polygon with greatest overlap. So one last application out there is being able to take a polygon and subdivide it in a topologically preserving way according to some rectangular grid. So I've used this to come up with, you know, an optimized point-in-polygon algorithm. I think there's probably other applications into, you know, chunking up data to do parallel processing. I'm not sure, but it's available from a command line interface that's bundled with exactextract. So that's what I got. You know, core geospatial libraries don't handle zonal stats. Here's a new implementation that I think is better than what's out there for applications I've seen. I hope to integrate pieces of this back into GDAL and Geos at some point, but it's kind of easier to develop outside of those too. If you're using it, or really for any raster processing you're doing, pay attention to your dataset chunking. Make sure you're setting your GDAL parameters optimally, or play around with them, and look at, you know, streaming your data so you're not using up your memory when you don't have to. So. I also want to say thanks both to NASA and the Army Corps of Engineers. They've both at some point supported development of this software, and I know that's not easy to do, and so it warms my heart to see federal government support for open source like this, so I want to thank them. That's it.